Imagine a moment when the voice of humanity falls silent. You are at a distance of 384,400 kilometers from the nearest living soul. Beneath your feet is the cold, dead regolith of the lunar South Pole. Above you is the infinite blackness of the universe. You have just finished installing equipment to search for water ice in the Shackleton crater, and you touch the radio tangent to report success to the Christopher Kraft Mission Control Center in Houston. But instead of the usual confirmation from the operator, you hear only emptiness. You check the antennas of the Orion spacecraft, you look through the terminals of the Gateway system, but all indicators of the Deep Space Network glow with a disturbing red color. Communication with planet Earth has been severed. Not for a minute. Not because of a technical delay, but forever. This is not simply a scenario from a science fiction horror film. This is a real strategic risk considered by analysts of the National Aeronautics and Space Administration within the framework of the Artemis program. What will happen if our technological umbilical cords are cut by space weather, a cyber attack, or an unpredictable anomaly in the structure of space itself? Today, we will dive into one of the most terrifying hypotheses of modern cosmonautics. We will analyze how laser and radio communication works in deep space, why the moon is a much more dangerous place for communication than we are used to thinking, and what astronauts will do when they realize rescue will not come because no one hears them. We will turn to reports from the European Space Agency, analyze protocols for autonomous survival, and learn the opinions of leading astrophysicists such as Neil deGrasse Tyson and Michio Kaku regarding the vulnerability of our civilization in the face of cosmic silence. Welcome to a detailed analysis of the eternal silence scenario, right where you are watching from. It is interesting to see how far our stories diverge. We begin. To understand the horror of a complete loss of communication in modern space, we must return to the origins, to times when silence was not an emergency situation but a planned part of the flight. In the Apollo program, which lasted from 1961 to 1972, every orbit around the moon was accompanied by a phenomenon officially called loss of signal. Imagine Michael Collins, the pilot of the Apollo 11 command module. In July 1969, while Neil Armstrong and Buzz Aldrin took their first steps in the Sea of Tranquility, Collins remained in orbit. Every time his ship went behind the far side of the moon, the massive bulk of the satellite blocked direct visibility of the Earth. For 48 minutes, he became the loneliest person in history. No radio broadcast, no telemetry, no communication with Houston. In his memoirs, Collins described this not as fear, but as a deep sense of separation from all living things. However, he knew. In 48 minutes, he would emerge from the shadow, and the voices of the National Aeronautics and Space Administration operators would again fill the cabin. This was a predictable silence. But history knows moments when silence became a harbinger of catastrophe. April 1970, the Apollo 13 mission. After the explosion of an oxygen tank, communication became the only thread holding the crew in this world. Every transmitted digit, every volt of voltage reported by the astronauts was critical for calculating the return trajectory. However, the most terrifying moment was the atmospheric entry procedure. Usually, radio silence during plasma heating lasts about 3 minutes. For Apollo 13, it stretched to 6 minutes. In the Mission Control Center, a dead silence reigned. Operators in Houston, tracking stations in Guam, and in the Australian Honeysuckle Creek stared at empty oscillographs. It was this moment that entered the textbooks of cosmonautics as an example of the fact that communication is not just an exchange of information, it is a confirmation of the very existence of the mission. Over the years, our dependence on data has grown exponentially. In 1963, the Deep Space Network was created, a global system of giant radio antennas located in Goldstone, California, near Madrid, Spain, and Canberra, Australia. These 3 points are located approximately 120 degrees apart, which allows the Earth to maintain continuous contact with spacecraft despite the rotation of the planet. We have become accustomed to the fact that the Perseverance and Curiosity rovers send high-resolution images, and the Voyager probes, which are outside the solar system at a distance of more than 24 billion kilometers, still respond to commands. This illusion of constant availability has made us vulnerable. If for astronauts of the past silence was a challenge, then for the modern Artemis mission it is a systemic collapse. Today's spacecraft, such as Orion, are flying supercomputers. They process terabytes of data that require constant correction from artificial intelligence on Earth and ground engineers. Loss of communication today means not just loneliness, but the inability to manage complex navigation systems that are not designed for full autonomy in critical situations. The moon is no longer just a dead stone ball. It has become a dynamic environment where every solar flare can sever this thin digital umbilical cord. And as soon as this happens, modern heroes of space will find themselves in conditions for which history has not prepared them. To comprehend the scale of a catastrophe in which communication is interrupted forever, we must first understand how complex and multi-layered the digital nervous system of the Artemis program is. This is not just a walkie-talkie in the hands of an astronaut. It is the most complex network that humanity has ever created outside the Earth's atmosphere. The heart of this system is the Orion spacecraft. On its board, several types of antennas are installed, each of which performs its specific role. The main communication channel operates in the so-called S-band and K-band. If the S-band is used for transmitting vital commands and telemetry, essentially reports on whether the engines are working and whether the astronauts are breathing, then the Ka-band is the broadband highway. It is through this band that ultra-high-definition video streams and huge arrays of scientific data are transmitted to Earth. The National Aeronautics and Space Administration developed these systems so that they could operate even under conditions of extreme temperature fluctuations and the radiation background that prevails on the way to the moon. However, the real innovation of Artemis is the transition from radio waves to light. The Orion Optical Communication System, known as O2O, uses lasers to transmit information. This allows increasing the data transfer rate dozens of times compared to traditional methods. Imagine the difference between an old modem of the 90s and modern fiber optic internet. This is exactly the leap we are making now. But herein lies a vulnerability. A laser beam is extremely narrow. It requires perfect aiming at a ground station. The slightest deviation of the spacecraft by a fraction of a millimeter due to a technical failure or collision with a micrometeoroid, and the beam of light will pass by the receiver, leaving the crew in complete darkness. The next critical node is the Lunar Gateway Station. It does not just orbit our satellite, but is located in a unique, near-rectilinear halo orbit. This strategic decision allows the station to constantly see the Earth, ensuring the role of a relay for astronauts working on the surface. When the crew descends into the craters of the South Pole, where direct visibility of our planet is often blocked by high cliffs and the edges of craters, it is the gateway that should become that space beacon that collects the signal and forwards it home. But here we face the main challenge of the lunar South Pole. Unlike the equatorial zones of the Apollo missions, where the Earth always hung high overhead, at the pole, our planet barely rises above the horizon. Any irregularity of the terrain, for example, the edge of the majestic Shackleton crater, creates a radio shadow zone. To maintain a stable data transmission channel, the astronauts of the Artemis 3 mission and subsequent expeditions will depend on the LunaNet satellite system, a project currently being developed together with the European Space Agency and the Japan Aerospace Exploration Agency. This is an attempt to create a lunar internet where every apparatus in orbit is a node of the network. What will happen if this hierarchy, from ground stations of the Deep Space Network to orbital relays, suddenly fails? Imagine that the chain is broken at every link. Even the most advanced signal processing algorithms will not be able to restore a message if physical carriers, radio waves and lasers, stop reaching their targets. We have built an incredibly fast and powerful communication channel, but at the same time, we have created a system where the failure of one key element can turn a high-tech mission into a group of people stranded on a hostile rock, hundreds of thousands of kilometers from civilization. When we talk about the loss of communication in deep space, we usually imagine a technical malfunction or human error. However, The real threats are much more large-scale and are embedded in the very physics of our universe. Why can such a perfect mechanism as the communication system of the Artemis program turn into silent iron? The first and most powerful enemy is our own sun. Although it is the source of life, for space electronics, the sun is an unpredictable aggressor. Astrophysicists, including Nicola Fox, who heads the Science Directorate of the National Aeronautics and Space Administration, have repeatedly emphasized the danger of X-class solar flares. These are the most powerful releases of energy, which in their strength are equal to explosions of billions of hydrogen bombs. When such a flare is directed straight at the Earth and Moon, it generates a stream of high-energy protons and electrons. These particles move at a speed that is a significant fraction of the speed of light and are capable of penetrating the protective shells of spacecraft. The result is a phenomenon that engineers call single-event upsets under the influence of radiation. One such proton, hitting a memory chip of the Orion onboard computer, can change the value of one bit of information. If this bit is responsible for the antenna pointing protocol to Earth, communication will be severed instantly. No, that is not the worst. A powerful geomagnetic storm, similar to the Carrington event of 1859, can induce currents in the antennas of the Deep Space Network on Earth itself, literally burning out sensitive receivers in California or Australia. In such a case, the astronauts will be perfectly fine, their instruments will work, but the ears of the planet will be deafened for a long time. The second risk factor is lunar dust, or regolith. This is not the soft sand we are used to on Earth's beaches. Due to the absence of wind and water that would round off the sharp edges, particles of regolith resemble crushed glass with incredible abrasiveness. In addition, under the action of ultraviolet radiation from the sun, this dust acquires a strong electrostatic charge. It sticks to everything, to spacesuits, portholes, and, most importantly, to the surfaces of parabolic antennas. The accumulation of even a thin layer of charged dust on the antenna feeds can distort the radio signal or cause an electrical breakdown in high-voltage transmitter circuits. Astronauts of the Apollo missions complained that dust penetrated into the smallest cracks. For Artemis, which is designed for a long stay on the surface, this becomes a chronic threat to communication equipment. We also cannot ignore the threat that we ourselves have created. We are talking about the Kessler syndrome, but on a lunar scale. Although there is currently much less debris around the Moon than around the Earth, the growing number of automatic stations, spent rocket stages, and CubeSats from private companies creates a danger. There is no atmosphere around the Moon to slow down debris and make it burn up. Any collision of a relay satellite with a small piece of metal moving at a speed of several kilometers per second turns this satellite into a cloud of shrapnel. A chain reaction could destroy the entire orbital communication infrastructure in a matter of days, leaving the crew on the surface without the ability to transmit a signal over the horizon. Finally, there is the most mysterious and at the same time most real aspect: cyber vulnerability. Reports from the European Space Agency regarding the safety of future missions state that space communication channels are becoming targets for a new generation of hacker attacks. If intruders or hostile state structures can intercept control of key ground stations or introduce malicious code into the software of relay satellites, they can block the signal or substitute telemetry. In such a scenario, astronauts will see on their monitors that everything is fine, while in reality, they will be flying into nowhere, and Houston will receive false reports of the stable state of the mission. Is our desire for maximum digitalization of space not our greatest weakness? We have created a system that requires thousands of perfectly coordinated factors for a simple Hello Earth to reach the recipient. It is enough for one brick to fall out of this scientific foundation, and the majestic project of humanity will plunge into the darkness of the unknown. What does an astronaut do at the very second they realize the speaker in their helmet no longer responds with the voice of the operator from Houston? This is the moment when training enters into conflict with primal human fear. The National Aeronautics and Space Administration spends years preparing for what is officially called loss of signal. However, there is a huge abyss between a temporary failure and the realization that you are left alone with an entire world. In the flight instructions of the Artemis program, clear algorithms of action are prescribed. The first step is the transition to return by default mode. If communication with Earth is interrupted during a critical maneuver, the onboard computer automatically executes a pre-calculated trajectory to enter a safe orbit around the Moon, or even to return home. However, these protocols are designed for the technical serviceability of the ship itself. If the Orion system is damaged, the crew must rely on the Autonomous Mission Operations Project, which is now being actively tested at the Johnson Space Center. This is a set of artificial intelligence tools that allow astronauts to independently plan oxygen consumption, calculate energy reserves, and perform diagnostics of systems without prompts from Earth. Effectively, we are trying to create Houston on board. But scientific data indicates that technical readiness is only half the battle. The psychology of isolation is a much more complex challenge. Dr. Albert Holland, a leading psychologist of the National Aeronautics and Space Administration who has studied human behavior in confined spaces for decades, notes, "The most terrifying factor is not the absence of help, but the absence of social reinforcement. When we look at the Earth from the surface of the Moon, we see everything dear to us in the form of a small blue dot. But when the voice in the headphones disappears, this dot turns into an indifferent object." To study this phenomenon, scientists use data from Antarctic stations, such as Concordia, which is called White Mars. There, researchers live in complete isolation for 9 months a year. Data from the scientific journal Nature indicates that prolonged isolation leads to changes in brain function. Cognitive functions slow down, irritability appears, and memory worsens. In the conditions of the Moon, where every mistake can be fatal, such a psychological state of the crew is a critical threat. We are used to the overview effect, a deep awareness of the unity of humanity that astronauts describe when looking at the Earth from orbit. However, in the scenario of eternal silence, this effect can transform into the alienation effect. A person on the Moon begins to feel not like a representative of humanity, but like a separate biological species abandoned in a hostile environment. Will the crew be able to maintain command unity when the hope for rescue disappears? In reports from the European Space Agency regarding the Artemis program, great attention is paid precisely to small group dynamics. In conditions of complete isolation, even a minor conflict over the use of resources or the choice of a survival strategy can lead to a split that will destroy the chances of rescue faster than the absence of oxygen. As we see, autonomy protocols are not just lines of program code, but an attempt to keep the human psyche from collapse. We build ships capable of flying themselves, but we still do not know how to teach the human mind to withstand the pressure of the infinite cosmic void without the thin thread of radio communication connecting us to home. When we find ourselves on the border between scientific fact and the unknown, questions arise that force the world's leading scientists to conduct heated discussions. If communication with the Artemis mission is lost forever, will this simply be a technical failure? Or does it point to a deep problem in our ability to become a space civilization? One of the most discussed topics in scientific circles is the role of artificial intelligence as a digital guardian angel. Famous physicist Michio Kaku suggests that future space travel is impossible without full transfer of control functions to autonomous systems. However, an ethical and scientific dilemma arises here. Can we trust artificial intelligence with the right to make decisions about the life and death of the crew when communication with Earth is absent? Imagine a situation where an algorithm decides that to save the ship, it is necessary to disconnect the life support system of one of the modules. Without confirmation from people from the Mission Control Center, such a logical choice may seem like an act of hostility to the crew. Debates around the autonomous morality of artificial intelligence remain open, and the Artemis program is the first real testing ground for checking these theories. Another aspect of the discussions concerns the theory of the Great Filter. This is a hypothesis that tries to explain the Fermi paradox. Why have we not yet met other intelligent civilizations? Some researchers suggest that one of such filters is precisely the complexity of interstellar or even interplanetary communication. If a civilization is not capable of creating a reliable communication system that withstands cosmic cataclysms, it is doomed to isolation and gradual fading in its local worlds. Is our vulnerability to solar flares and cosmic radiation that very barrier that stopped thousands of other civilizations before us? Also, scientists still do not have a consensus regarding the so-called lunar plasma anomalies. On the night side of the moon and in the regions of the South Pole, the solar wind interacts with the surface, creating complex electromagnetic fields and clouds of levitating dust. Some models show that these fields can work as natural jammers for certain radio wave frequencies. We still do not know for sure how a high-frequency signal will behave in deep, eternally shadowed craters. Could it be that the nature of the moon itself hides physical processes that make stable communication in certain points simply impossible? These scientific debates emphasize the main thing. We are still at the student stage. Every theory about why a signal might disappear is a step toward understanding how to make humanity truly protected in space. We are not just building rockets. We are trying to break the code of cosmic isolation that has been in effect for billions of years. And if the Artemis mission faces eternal silence, the answers to these questions will be sought by next generations, analyzing our mistakes through the lenses of the most powerful telescopes of the future. How can we prevent the scenario of eternal silence? Humanity is not used to giving up in the face of technical limitations. Even now, while the first ships of the Artemis program are only preparing for launch, engineers and scientists are already developing technologies that should transform the moon from a radio silent zone into a full-fledged digital outpost. One of the most ambitious projects is the Moonlight Initiative from the European Space Agency. Its goal is to create a lunar constellation of satellites that will provide stable communication and navigation similar to the GPS system on Earth. This will be a real lunar internet. Instead of each mission relying on its own antenna pointed at Earth, astronauts will be able to connect to a local network. This means that even in a deep crater or on the far side of the moon, the signal will be transmitted from satellite to satellite until it finds a path to a relay that sees our planet. This creates redundancy. If one node of the network fails, the system will automatically redirect data through another. But what if the problem is deeper? What if the nature of radio waves themselves limits us? Here, quantum physics enters the scene. Scientists from the National Institute of Standards and Technology and researchers from the Japan Aerospace Exploration Agency are working on the concept of quantum key distribution and quantum communication. Although we cannot yet transmit complex messages through quantum entanglement instantaneously, these technologies promise the creation of communication channels that are impossible to intercept or jam by traditional methods. Quantum communication does not fear solar flares as much as conventional electronics do, because information is encoded in the states of light particles themselves. Photons. This is a technology of the next century that could become a lifebuoy for interplanetary travelers. We must build infrastructure in space even before we send a large number of people there. Safety is not only a strong ship hull, it is the reliability of information exchange, notes Josef Aschbacher, Director General of the European Space Agency. But suppose the worst has happened. Communication is lost, autonomy systems cannot cope, and the Artemis crew is stuck on the surface. Does a rescue plan exist? In modern space architecture, the concept of rapid response begins to operate. Companies such as Elon Musk's SpaceX are developing the Starship system not only as a transport vehicle, but also as a potential lifeboat. Thanks to the possibility of refueling in orbit, a fully autonomous cargo starship can be sent to the moon in record short time. On its board, there can be not only supplies of oxygen and food, but also mobile communication stations that can be dropped onto the surface to restore contact. This is a cardinal change of paradigm. We are moving from an era of single missions to an era of space mutual assistance, where state agencies and private corporations create a joint rescue protocol. The future of communication in space is a struggle against infinite distances and unpredictable physics. We are learning to build networks that do not break and create ships that know how to return home even when voices from Earth fall silent. This is a technological evolution that makes us a true space species capable of surviving in the ocean of stars, despite any obstacles. We are approaching the moment when science meets eternity. Imagine the last hours of the crew on the surface of the moon. Oxygen tanks in the life support system show critical numbers, and the radio broadcast remains dead. In this scenario, the astronauts of the Artemis mission become not just researchers, but witnesses to the greatest isolation in the history of our species. In the 85th minute of our analysis, we see desperate attempts to signal. When digital systems fail, a person returns to the basics. Astronauts can use laser communication systems in manual mode, trying to point a narrow beam of light where a blue ball of Earth hangs in the black sky. They know that somewhere there, in the laboratories of Madrid or California, their colleagues are peering at every change in the brightness of the lunar surface through the lenses of giant telescopes. Every flash is a coded "we are still here." This is a dialogue between two worlds conducted in the language of light when the language of digits has fallen silent. On Earth at this time, tension reigns that is impossible to describe. The National Aeronautics and Space Administration deploys all available resources. The Lunar Reconnaissance Orbiter changes its trajectory to pass directly over the landing site, trying to take high-resolution images. The world held its breath. This situation demonstrates to us the main lesson. Despite all our technological greatness, we remain vulnerable in the face of cosmic scale. 384,400 kilometers is a short distance for a radio wave, but an insurmountable abyss for a person without a reliable communication channel. The philosophical conclusion of this story lies not in defeat, but in the price of progress. Every great geographical expedition of the past, from Columbus to Magellan, was accompanied by months and sometimes years of uncertainty. We simply forgot about this feeling in the era of instant messages. Loss of communication with the Artemis mission reminds us that space exploration is not an entertaining walk, but an existential challenge. It is an act of bravery where the risk of being heard or remaining in silence is part of the agreement with the universe. What does this hypothetical tragedy mean for us? It is a call to action. We cannot afford to stop because of the fear of silence. On the contrary, it is an incentive for the development of an even more powerful infrastructure, investing in laser networks, quantum communications, and the creation of international rescue protocols. Our destiny is among the stars, and the path to them lies through overcoming darkness and silence. We look at the last frames of our video. The crew looks at the Earth for the last time. It is so small that it can be covered with the thumb of a hand. But it is there that everything they love is concentrated. Even without communication, this visual contact remains the strongest connection in the universe. We are a species that strives for knowledge, and no silence will be able to stop our desire to find answers. Dear viewers, we have analyzed one of the most complex scenarios of the future. What do you think about autonomy in space? Are we ready for the fact that the first colonizers of other worlds will be forced to rely only on themselves? Is the risk of eternal silence a justified price for humanity's step into the unknown? Share your thoughts in the comments. Your ideas and discussions are also part of our common path to the stars. Thank you for being with us on this journey through space and time. Subscribe to the channel so as not to miss the next scientific investigations. Until we meet in the boundless universe.